Alright,
we're on. Good.
Take one.
Alright, so to do a slight rewind. Hey, focus. You look a little tired today. You ready?
Yeah, you like.
We could play a game.
We should play a game.
A quiz is just a great way to start a morning.
Jeremiah, we should play a game.
Reactant forms product. Reactants form product. So, we have got to this point in our chemical life in which this idea is now got to be kind of, I don't know, we got to shake it a little bit. Because in theory, not in practice, and we're going to find out why today. In theory, this is really, and I think you kind of get this idea. I mean, once you hear it, if A and B go to C and D, then there has to be maybe a world somewhere out there or some environment out there where C and D, where it would be able to do what? Form A and B. In other words, that the backwards, we call it the reverse reaction, should be able to take place. In fact, we have probably our most famous chemical reaction that we have.
E equals MC squared.
Chemical reaction. That's formula. It probably is the most famous formula. But for a high school student, well, as soon as I start writing this down, most of you will start to get the idea of where we're going. Does anybody know the product?
Photosynthesis.
It's almost game time?
It's game time, guys.
Well, this isn't photosynthesis.
Cellular respiration.
This is cellular respiration.
Taylor. He knows.
But we do know, like this makes sense, at least it makes sense to me because we've seen this before, okay? We've seen sugar, and I've shown you because I've blown up a gummy bear or an M&M or something like that. We'll do it again. We know that if we breathe in oxygen, we can take that sugar, we break it down into H2O and CO2, but we also get the energy, and we harness that energy. But we also know that plants on this planet do this. Yay!
Woo!
Wow!
That's so interesting.
We do have, these are not written correctly because what are they missing? They're not
It's not balanced.
balanced. We know how to balance this chemical reaction because you've seen it numerous times. So,
Did you have it balanced last year? No? Yes?
yeah, they didn't have to balance it. I gave them the balanced chemical reaction. So, here is a reaction that happens on Earth that is fairly complex, but we can easily see that A and B make C and D, but there is a process, there's too much talking in this area of the classroom, there is a process on Earth that allow C, I guess you could say C and D to make A and B. All right? So in other words, we know that it's happening. Let's make sure we.
It happens in class. Okay,
There's the.
we figured this out in homework.
I knew that April 1st would bring something.
And then Duck Duck Goes.
That's pretty good.
Outside. I love that. Figure this out in homework. I would just go stay seated.
Look, we write a really complicated thing and act like they missed it. Yeah.
I'm not going to act like anything. They're going to have to go and watch the video.
Okay.
I can easily.
Oh, this is
teach-
gonna be fun. Let's go.
I can easily teach to
Can
nobody.
we close the door and lock it out?
Because sometimes I feel like I do
Can
that
we close the door?
anyway.
You have half the
It's
class
really
this
fun.
year.
Yeah, a
It's
lot of us
the-
are trying.
I know you are.
I ain't trying.
So here we go. So this is a process in which, of course, the reactants can form products,
Oh,
and
we're
now we
supposed to
can
be writing
see
this down,
the
right?
products can go, you can write this one down or not.
Would it be useful? though?
It's trying to get the idea of what is going on. So,
I think the best part about this was Sophia at the start.
Yes, that was absolutely horrendous when we practiced. Where's the conference?
Don't talk and get done by you.
She's out the window.
I thought she was just giving me a standing ovation.
The conference was just out the window and had a no kill. She was like,
We need more like points.
All right, reset.
why did you not go?
So,
Why did you not go? You always.
we do have a new note, by the way.
It is part of the
Chemical
demo.
equilibrium.
It's
In
on your notes from your
Theory. Preston, notebook out. And at very least, for 10, we're taking notes.
That's what Seawood says.
So,
What are you supposed to take notes on? His life stories?
Yeah.
Okay.
Have you seen my pictures?
We'll do better next
Pretty
year.
good.
that's enough, that's enough.
Better coordination next time.
No, it's true.
We can only plan it weeks ahead.
I don't even
Yeah,
have
me
our
too.
normal class, and we don't even get anything.
Hey, there's
to
always
show.
next year.
Either, like, we show-
So I'm going to write this general formula.
Literally.
Yeah, let's keep our class demo notes over here.
She was shaking.
And I'm going to write this here. All right, again, that's a general reaction. It can mean any amount of reactants and products. Here's what you're going to see, and you get to learn a new symbol. In theory, all reactions, doesn't matter what they are, in theory, all reactions are reversible. And so you get this new arrow that has one going one way that we're used to, but the reverse reaction can also take place. Now again, this is in theory. Why, can anybody just guess why in practice we don't observe this all the time?
Well, because when you bake a cake, you can't just take the ingredients back out.
Well, in theory you could.
In theory, but you can't.
Okay,
Because it's already combined.
But you can't.
no?
You can't.
How about you guys?
You guys, look, believe it or not, baking can maybe help us get to the right answer. What do you got over there, Jack?
I'm just imagining, okay, I have a pile of ash and I want to try to unburn it. Like, all the energy is inside.
Okay, we've lost energy.
Yeah.
Okay, it's hard to put back energy, but remember, energy is conserved also. It can't be created or
But it's
destroyed.
like in the
So it's still there.
But it's hard
Alright.
to like create that.
We're getting somewhere here. It's getting close. Bennett?
Are you losing like parts of the substance when the reaction actually occurs? Like, is there just like waste that's left over when the reaction occurs?
Well, again, we know that mass and energy are, everything is conserved. The mass at the beginning has to be the mass at the end. The energy at the beginning has to be the energy at the end. Now, granted, things are lost and they get released and all that other stuff, and we do have this thing called entropy that's moving everything towards disorder. So there are things working against it, but it really has to do with, to be perfectly honest, it has to do with the environment. In other words, we're on Earth, and on Earth we have a really restricted environment. I think everyone here would agree that the Earth environment is different than the environment on Jupiter. And the Earth environment and Jupiter's environment is definitely different than the environment on the Sun. And guess what? The chemistry is different on Jupiter. That would happen on the surface of Jupiter, and definitely the chemistry that would happen is different on the Sun. And so the point is that we have a very restricted and actually very narrow temperature range, pressure range, all of these things. The surface of the Earth has this very narrow range, and in that narrow range, the chemistry is often, for instance, burning of wood. The chemistry will often go in one direction. I know in theory you should be able to take all that energy from heat, and in theory you should be able to take all of that extra mass in the smoke that gets and mix it up with the ash and the carbon and put in the oxygen and the water back in, and you should be able to make wood again. In theory, for sure. And so this idea, believe it or not, God taking water and making it into wine, like, that's not hard. Why? Because all he has to do is rearrange the...
Let's just discount America.
All I do is really from.
No, he just tells it to and it
I'm
does
not
it.
discounting it. All I'm telling you is that God has the
So we
power
can all do
over
that.
electrons,
He knows the chemistry.
protons, and
But
neutrons.
he all he's got to
He
do
could
is
just-
just tell it to
chemistry
do
class.
it, and then it just does it.
He made it.
Yep. It's just like, oh.
But that does show you that, yeah, we can't all have questions.
We just now started doing that.
That does show you that at the very least,
Oh, more work.
Oh.
Whoa.
Varied, are we? Reverse. Oh my. Oh, chill.
Yeah, I got an actual.
all right, let's go here.
She actually the chemistry at the bathroom.
Do you need
Yes.
to go to the bathroom?
Go out.
Leave. Sure. You could have gone while you were out
We were playing
on your
Duck Duck
protest.
Goose, but that wasn't.
Our protest.
Rocky.
So if Elon Musk hurts like a group of humans on the moon, or not the moon, Mars, would the chemistry there be a lot different? Right?
Yeah, okay,
Would
first
they
of all,
teach
let's make sure we
chemistry?
understand what I mean. The chemistry would be different. Like atoms, protons, neutrons, electrons are the same pretty much everywhere in the universe. The problem is that the same reactions wouldn't be taking place because you go at completely different temperatures, completely different pressures, completely different environment. So yes, the chemistry on the surface of Mars would be different. But you got to remember, if we're going to inhabit, especially planets in our solar system, it will not be because all of a sudden we adapt in a way that we can go live on Mars.
Yeah.
They don't have the oxygen to breathe. They don't have the pressures that are necessary. You know, if you were exposed to the surface of Mars, you would die very quickly. So how would we do that then? Well, we would put like a biosphere there. We would build a environment that's very much like, guess what? Earth. And so the chemistry would be the same.
Wouldn't that be technically like trying to play God though?
No. Just building a biosphere
I mean, it's the same thing as wearing a spacesuit.
or going in a
It's just a
submarine.
really big spacesuit, or like.
You know,
It's just a really big
it is.
suit.
I mean, we do it here on Earth. We live underwater.
We do?
Why is this a
Submarine.
I'm living underwater right now. There's water.
What's the deadliest purple
There's
element?
water in this.
Here we go with, we're gonna start our, I need this filled up like halfway or so.
I think that's
Wait, you're. No, no, that's dirty. That's
You're
dirty.
giving it to those activists?
It was yellow. It's yellow.
This is Brookhill Pure.
Oh my gosh, is it like yellow on the bottom?
could get
Why'd you cross out this still?
Because,
It's not distilled.
as you can see, and I'm, just
I
like the things we've been discussing, we have different environments here. I have yet to make the hot environment, but we have a room temperature environment.
Come on, brother.
We obviously have a, or going to obviously have a hot environment. That doesn't need, you don't need to move.
Oh. Never mind that. Hello, YouTube.
Like it's
But-
YouTube, welcome.
So I'll stick this one over in the cold environment. There are some interesting things that happen. with this.
Why is it
What's the purple? It's purple.
Well, this is cobalt 2 chloride at room temperature.
It's so pretty.
What we're going to find out is that this actually has a different ionic form. And it can actually change to cobalt 4 chloride. And so the cobalt ion can lose and gain different electrons, and in that process, I think we will see a obvious change.
Changing colors? Kind of.
Well, it's already, yeah, that one definitely is. And we'll see how long it takes that one to do it.
You want this filmed?
When it takes a minute. Well, the water's got to warm up a little bit.
We're
The
just trying
cold
to be
water is
professional.
already. You can already see a definite difference there already.
Oh wow.
What's in that?
Cobalt 2 chloride and cobalt.
Is that one of the
4
purple
chloride.
elements?
Can someone look at the can I lick it?
Yeah, is that one of the purple or like red?
I mean,
Cobalt. Cobalt looks like it's gonna be okay. Oh,
Can we try?
the metal.
Oh,
The salt. Yeah, you don't want to ingest the salt.
I think it's okay.
it's only one
Are
way to
you
find out.
challenging
Yeah,
That theory.
it's only one way to find out.
Preston, you're up. I'll be fine. I'll be fine, okay?
Yeah, I feel like Chris
I'll drink it and I'll be totally fine. I can guarantee you that.
I don't like that. All right, we already kind of know these
That's
notes.
who's drinking.
These notes right here are molarity notes. Remember that concentration has to do with how much of a substance you have in a solute. So it actually means it's a percentage of something. In other words, this is not pure cobalt chloride. I have that in the back. That salt is a completely different salt.
You know, everyone
This
has that.
is a solution of cobalt 2 chloride. And we're starting to get some warmth here. This one I should have probably started a little earlier.
Yeah.
And we already got that note. You don't really need that. You don't need that either. Don't need that. Now, that's a good note. So since you already have these notes, then this actually makes a little sense. The greater concentration of something, the more likely the reaction is going to proceed. Can anybody give me a guess why more the concentration, the more likely a reaction will proceed? Trying to use our brains here from what we know about how kind of reactions go.
Well, if there's more of a substance in one spot, there's more likely a chance for that substance to react to something else, right?
I like it. I like it. I like it. Remember, when we talked about activation energy, and when we talked about especially things like kinetic molecular theory, we know that atoms are constantly doing what?
Moving.
They are moving. And so what we believe is that these atoms actually have to hit each other. It's called the collision theory. They have to hit each other in the right way to move forward. All right, I'm starting to hear some boiling, and we're starting to see a definite color change. And actually, this one right here is one of my favorite colors. So if you go to a store and say I would like a cobalt blue color for a car.
Is that why the color is
Man, with that, I like to think it is.
I mean, that's a really kind of cool color.
Isn't that like a myth feature?
So here we have our 3 room temperature, we have our ice, and we have our.
Wow.
Now, this is, you're going to see, again, this is a reversible reaction. So here goes that one. I'll go ahead and we'll keep room temperature. And I'll put that one in there.
reversible then.
It's your con. It's
Whoa, it's like changing color.
Whoa! Show the camera.
It's a plan.
Yeah.
Hold on. Look at it.
Now there is an interesting thing, and I really don't know the reason. I don't know why this happens this way, but you will notice, and I'll reverse these a couple times, that the cobalt chloride, when it gets to the 4+ to the 2+ ion, they switch. This is going to turn pink from the bottom up. This will turn blue from the top bottom, and I have no idea why.
That's my question.
It will always do it.
Because heat rises.
And people just don't know.
I don't know if anyone's done the science on it.
Why?
When the first time I noticed
People need
this,
to know.
the first time I noticed it, I looked up the science on it, and there was nobody really doing anything. So
Why aren't you doing it though?
I really want to.
I don't have time. I barely have time for this. So here we go again.
Oh, whoa. Looks like
And
Kool-Aid.
You will now have it go pink
That's sweet.
from the bottom up and blue from the top down.
You could really make like a really cool lava lamp with those.
If you were able to kind of separate them, it would probably be pretty
Can I drink it?
It definitely has something to do with the heat and how it works, but
Can I drink it? I really want
let's visualize the reaction.
Do they go back to room temperature? I mean, I guess that would take a while, but do they go back to that original color?
Yeah, once we get it back, it'll go back to the original color. Here it goes. Let's visualize the reaction. And I think you guys get this. At the beginning of a reaction, so I'm using this right here. At the beginning of the reaction, right at the start, and again, I know these things happen in split seconds, but at the start, is there even C and D around?
No.
No, there are no products. So that means A and B, the reactants, have very high concentrations. So at the beginning of a reaction, the concentration of the reactants is very, very high. At the beginning of the reaction, we have, and I'm just going to kind of walk through it this way, lots O. A and B. And no C and D. I think that makes sense. If you put these notes down, I would just actually use my notes that are on the monitor rather than this. This is just going to help you guide through. So A and B are very high, and according to this note, the greater the concentration, the more likely a reaction is to proceed. Well, if there's lots of A and B and no C and D, well, we know the forward reaction is going to be, we're going here. I guess we're boiling. We're getting close.
It's darker than it was before.
Yeah, we're finally got the heat in the right spot.
I think it's about to go boom boom.
So here is our
It's about to go boom boom. It's boom.
it is really actually a cool color.
I like that color. It's great. It's very drinkable.
And again,
It looks like
I'm gonna put the blue into the ice
Is that
bath,
a mini Gatorade?
the pink into the heat bath, keep room temperature. I can keep reversing this reaction
Justice for
until,
room temperature.
and notice it is the environment that's causing the reaction to turn. I'm not doing anything else. I'm changing its environment.
That's actually good.
I'm a cheese.
So if anyone's ever seen Sleeping Beauty, make it pink.
What a good movie.
Make it blue.
Yeah. I've seen the references that were not really good.
Oh, come on, Disney.
Sleeping Beauty is like not even.
I mean, I saw her, but she was like, so.
All right, now C and D might be low, but guess what's happening though? They're starting to do what? Yeah, they're starting to build up to their concentrations. Yes, Sophia. Oh,
Can I use the restroom?
where are we on time? I think this might be close.
It is 24 o'clock.
10 minutes. Sorry, you know the rules.
No, actually, just under 10 minutes.
Yeah, it's on the
Just
safe
under
side.
10 minutes, so we definitely can go.
It's
No,
That's
no,
not
just over.
Charlotte.
Just over, they said it wrong.
It's like 11 minutes.
No, nice try.
What you get? No.
It's 9.
Maybe you're wasting time.
That's true.
I can tell you.
So,
So,
There's 12 minutes.
as the reaction continues, we can kind of see in our brains, hopefully, that A and B concentrations will start to dip, and C and D concentrations will start to rise. So I'm going to count that as a step 2. A and B go down, and C and D start to build. Any questions right now in our brain?
Can I go to the bathroom?
No.
Yeah, I mean, you did ask.
Now, for the reactions that you guys have seen up to this point, this would pretty much be it. A and B make C and D, right?
Yes.
But we now can see right here in front of our very eyes that that's not how all reactions work. There are reactions that can actually go in both directions. In fact, what I'm telling you right here, right now, here's our room temperature 1. It looks like nothing is happening, but you have to know, and you're going to find out in about 5 minutes, that there's a ton of things going on right now in this test tube.
That you don't know about.
No, it just has to. Why? Because right now, A and B are making C and D. This is obviously a reversible reaction. And C and D are making A and B. It's just doing it now at the same rate, and you can't see the change. But is it going on? Yeah, that chemistry is going on. It will go on for as long as I have cobalt-2 chloride in this test tube. Why? Because this is, as you can see in front of you, a reversible reaction, which means it is A and B are making C and D. C and D are making A and B consistently and constantly. This just has now reached, at room temperature, this has reached a state of equilibrium. And you will not see the change. And so that's what's going to happen. Here's what's going on for a reversible reaction. There's going to come a time where C and D are high enough that they're going to do what? They're going to start doing the reversible reaction. So, step 3. Soon, and this is the important part that you need to put in here, and I'll put a little star right here. For reversible reactions, soon C and D will be high enough to make A and B. Before somebody broke the springy seesaw thing in the back, that is actually a pretty good visual of what's kind of going on. There's this battle between reactants and products. And if you stop shifting your weight on the spring, soon it's going to reach a state of equilibrium. That doesn't mean it's equal. For instance, if somebody that were a little bit larger was sitting on one side of the spring versus someone who's a little bit smaller sitting on the other side of the spring, how would that apparatus end up when it finally stops? It would be tilted in one direction. But it would finally stop if you stopped moving. But of course, if you shift your weight again, you can get that thing tipping one way or the other. that is really what's kind of going on right here. We have a little chemical seesaw going on. In this environment, this is the equilibrium, and we can see it by a color change. In the ice environment, this is the equilibrium, and we can see it by a color change. And at room temperature, this is the equilibrium, and we can see it from that color.
What if we change the temperature of the room?
Soon, and finally, we will get a state of equilibrium. But, all right, make sure everyone's writing, because this is a huge point. But, and I think you can see it in front of you. Just because it says equilibrium does not mean everything's equal. It just means there's that constant, that consistency. That means these reactions have moved in their environment to a place where they're going to you're not going to see a difference. So in other words, I think it's this next note.
Wait, what?
This is the next note. Did you need it back?
Yeah.
That's fine.
Thank you.
Yep. And that will be our last note once we get to it. Are you going with a different notebook method?
I can't find it. I think it's in my backpack. We'll see.
So, you do realize that it's this piece of loose leaf that you have to study for Monday's quiz.
It'll go somewhere safe. Don't worry about it.
I trust it.
You have a lot of these.
We are.
Paper.
Did I hear insults? I didn't hear it, but
No.
no insults.
Wait,
All right, are we good?
No.
She's red.
Wait, can I finish on the next page? Yeah. This page is.
Oh, we still got a little ways to go with equilibrium. You can start a fresh slice. No reason to cram.
Next page.
Slow your roll.
Alright.
I see pencils down. Now I have to move. I've been shooed away.
I need to drink my sweet tea.
You've already had one of these.
I have to get my 3 liters in. It's my drinking goal.
I was about half heart failure.
And so, notice what is equal. It's not that the concentrations are equal. It's not that everything is balanced out. The what is equal is the rate. At some point, the rate of the forward reaction will equal the rate of the reverse reaction. And so, what you have to see is you won't see an outside change, but there will be this dynamic change going on. So I'll let you write that down. Hopefully be able to.
6,000.
Gosh, Rylan.
Let's go, Rylan.
Give him a 0.
You really hurt the teacher.
1 minute.
It says 1 minute. Well, we got a full minute. Thanks, Caleb. Caleb's always watching out for you guys.
Thanks, Caleb.
We love you, Caleb.
Thanks, Caleb.
He's like, 1 minute. Don't you dare go over. This is over, man. Had enough.
Yeah, your alarm's going off.
Do you want to stop filming?
Yeah, we might as well put it.
Oh,
Alright.
did we get Leslie or getting hit by the
Subscribe.